my goal is to get that done today. So basically, the divergence test says that you can find this particular kind of surface integral called the flux by converting into a triple integral. And if you imagine the surface S enclosing a volume called E, then the triple integral over this volume E of the divergence of f dv is the same as this surface integral called the flux. And the divergence is this. So here is our first question. Number 9, my goal is to get through them all, hopefully, up to, I think it's 15. And that'll be today's done. So here is our vector function. The region E is bounded by z equals 25 take away x squared take away y squared, which I believe is some kind of paraboloid, and the xy plane. Now, we need to generate the limits of integration. Typically x, y, z, but sometimes won't we do polar? Depends on the situation, right? So I'm looking at z equals 25 take away x squared. And so that kind of tells me the range of z's. And when they say the xy plane, that means z equals 0. So if I was looking at this, I could say, well, it's going to go from 0 to 25 take away x squared take away y squared. And then I have to figure out, well, what's going to be the range for the x's and y's? So if you take this guy and you put him on the floor, z equals 0, then the relationship of the x's and y's ends up being this one. Does that not scream out polar form? Great. So I'm not going to go this side. I'm going to go that side. Now, it's a complete circle. They don't make any in the first octant or any kind of constraints like that. And it's a circle of radius 5. So that gets me those two guys. And the z still goes from here to here. But instead of 25 take away x squared take away y squared, right? Instead of 25 take away x squared take away y squared, can't I rewrite that as 25 take away r squared? Are we comfortable with the limits of integration of this surface here, right? A z and a z0. So we're going to now find the divergence of f, which is basically differentiate this guy with respect to x, differentiate this guy with respect to y, and differentiate this guy with respect to z. And so what do I get? I get 3x plus 1. But if you put the whole package together, then we should be able to get the flux. Surface integral of f ds. And it's going to be a triple integral. And I'm going to do, what am I going to do? I guess I should check this guy. So z equals 0 to z equals 25 take away r squared. Then I'm going to do r equals 0 to r equals 5. Then I'm going to do theta equals 0 to 2 pi. And then the function I'm going to do it to isn't actually 3x plus 1. Won't it become 3r cosine theta plus 1? Are you happy about that as well? Right. Everything gets converted into the polar equivalent. So this becomes 3r cosine theta plus 1. And then it's going to be an r, a dz, a dr at least, and a d theta. Are we good with the setup? Right. The region turns into a polar setup. The divergence is very simple, but still converted into polar. I'm doing it z, then r, then theta. So, and I didn't forget. I'm glad to say that, guy. It's not going to be very pretty to do this question, but from what I'm looking at, I'm just scanning, I just think it's weird powers of R, right? And then the next time round, it's just going to be integrating a cosine. So I don't think it's that bad. So dot, dot, dot. Set one out the way. So question 10, same question, find the flux. This is our vector field. S is bounded by x plus 9 and z equals 0, and this fella. And this is another example of, well, when you talk 3D, I should really be calling it cylindrical coordinates. So when I was saying earlier polar, I was really talking about that, but essentially it's...
Excuse me, is that a
Yes.
9 or a 4 in front of the XYZ? XY squared, Z squared, what's the...
Yeah, that's a 4. That's a 4.
Thank you.
Right, so what we have got is R, theta, and Z. We call that cylindrical coordinates when you use that combination. This thing here is pretty much a giveaway. 0 to 2, 0 to 2 pi. And Z is going to go from 0 to x plus 9, which is R cos theta plus 9. Are you happy about the limits of integration of this and that? Right. There's your Z's, and then that basically generates these two guys. So our flux, which is this fella, is going to be a triple integral of, do the Z's. Well, I should check here which one goes first, which one goes second. Yeah, it's the right order. Is it? Let's check. Blah, 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 blah. Yeah, okay. Z equals 0 to Z equals R cos theta plus 9. And then I'll do the R from 0 to 2. And I'll do the theta 0 to 2 pi. In here is going to go the divergence. Okay. If you differentiate this with respect to x, you get 4x cubed. If you differentiate this guy with respect to y, you get 0. And if you differentiate this guy with respect to z, you get 4x y squared. And I'll just skip the limits integration. It's the same guys again. 4x cubed. Good grief. That's going to be 4 r cubed cos cubed theta. And this guy's going to be 4 r cos r squared sine. So it's going to be that guy.
I feel like this one would be better if you took out a 4x.
Oh, just suck it out.
Suck it right on out.
Okay, let's see what that gives you. You got a 4x. Ah, you get the biscuit. Would you look at that? Didn't even see it. 4r cos theta, and isn't that just r squared? So you get that. Oh, with the other r, so you get that. So that whole mess that I was going to have to fight my way through, who knows how many lines, ends up just being this fella. So 4 r to the 4 cosine theta. Do the z's, do the r's, do the thetas, and the z's are going to go from 0 to r cos theta plus 9. So pulling out the 4x just was a really cool piece of algebra, because everything in there just turned into that when you add the extra r. Now it does mean, yeah, let's do one of the integrations because that is going to be weird. So I'm just rewriting these two again, untouched. I'm going to integrate this with respect to z, which doesn't actually do that much, except stick a z on it. And the z is going to go from 0 to r cosine theta plus 9. And then we can do the other two guys. So I have a 0 to 2 pi going on, I have a 0 to 2 going on. Now, if you stick in z, you get 4r to the 4 cosine theta times z, which is that guy. Take away nothing. So that becomes, well, multiply this guy, you get 4r to the 5 cos squared theta. And then you get 4r to the 4 over 9. So you get 36 r to the 4 cosine theta. And you're going to do a dr and a d theta. Let's just keep going then. You're going to add 1 to the power, which is 6. So you're going to get 2/3 r to the 6 cos squared theta plus 36/5 r to the 5 cos theta, evaluated at 0 to 2, and then you'll do the thetas. 2, 4, 8, 64, 1/28. 2, 4, 8, 16, 32. Nobody in the right mind's going to do 32 times 35. 1120. Let me check. That's going to be one really.
Is it 35/5 or 36/5?
It's 36, which is going to change that top number, isn't it? So 36 times 2, 4, 8, 16, 32. Okay, that's 1152/5. Okay, according to them, the answer's going to have a pi in it. Where on earth is the pi going to come from? Oh, okay. Believe it or not, this is right. Okay, well, I'm not going to take it. I'll tell you what they say. This is going to be 128/3 pi. I'm a bit unsure where the pi is. Oh, it's going to come out with somewhere here. Okay. That guy is just basically going to be sine theta with a really ugly fraction. What's this guy going to be? How am I going to integrate cos squared theta? Forget about the 128/3, like you can worry about later. Cos squared theta, how am I going to get that?
Use trig
I see.
identity.
Okay, anybody got the trig identity for it?
And this is actually where the pi is going to come in. It'll be 1/2 plus cosine of 2 theta over 2.
1/2, that guy, right? And that's where the pi that we talked about does come from. Okay.
You forgot the 2 theta, although that doesn't necessarily matter because that will just go to 0.
Right. Okay, but you'll get it. Okay, so it's correct. Ugly as heck, but works. Bit surprised that I actually, with one hiccup, got to the right place. Let's just take this one as far as what the integral would look like. So I've got this fella and this guy, and somehow I've got to generate what the solid would look like. So it's a z equals x squared plus y squared, and it's a z equals 9. Well, one of these guys is bigger than the other. And from what I can see, the 9 is the big one, and the x squared plus y squared is a little one. If ever you see x squared plus y squared, what should be going through your head as far as variable names are concerned? If you see x squared plus y squared, do you think I'm going to do x's and y's?
Are we going to use R and theorem?
Right. So I'm going to go and make that 9, and I'm going to make that r squared. Are you comfortable that that's what z would look like in terms of r? Problem we've got now is to figure out what exactly the r and the thetas are, because we're essentially doing cylindrical coordinates yet again. And I've got this guy, and I've got this guy. If you put them together, don't I now have that guy? And if you put that, now don't we have our limits of integration? And we should be able to get the divergence. Let's see what that looks like. Maybe it's not as bad as it seems right now. So I'm just double checking as I scan here. It's cos z and an xy squared. If you differentiate that guy with respect to x, all you get is y squared. Now, if you take this middle term and you differentiate with respect to y, you don't get anything. And if you take this end guy and you differentiate him with respect to z, you just get that guy. And guess what? It ends up being a really nice answer. I mean, superficially, would you look at how ugly that is as a vector field? But isn't it very nice as a divergence? So we should be able to do our triple integral. Z is going to go from r squared to 9. R can go from 0 to 3. And theta can go from 0 to 2 pi. And our divergence is r squared times an r dz dr d theta. And if I planned ahead, I would have realized that I could have saved a little bit of work by just doing r cubed. But you can do that, integral's not that difficult, right? So we'll do a dot, dot, dot on that one. So I guess the moral of this story is that when you're doing the divergence theorem and you're trying to create limits for x, y, and z, that if there's an x squared plus y squared or something like it floating around, you should think polar, or to be really exact, you should think right, finally got the word, cylindrical coordinates. You should think cylindrical. And it hasn't harmed yet, but shouldn't we also do that rule that Terence told us on Friday? Shouldn't you find the divergence first, just in case the answer is 0? None of the questions have been, but it's worth a try, isn't it? So I think I'll do the next one that order. It's going to be what, number 13? So find the divergence before we do anything. Differentiate this with respect to x, and you get 3y squared. Differentiate this with respect to y, you get nothing. And differentiate this with respect to z, and you get 3z squared. And I'm going to call this 3y squared plus z squared. And this is the first time we've ever done a cylindrical coordinate orientated in a different direction. Don't you normally do x squared plus y squares makes a circle in the floor and z is the up guy, right? But z is no more up than x or y is. So you can actually do polar on these guys. Right? So I have basically a circle in the YZ plane. And my X values go from -3 to 3. So if you think about how I would incorporate that into my limits of integration, how about X goes from 3 to -3? Okay. And how do you do a circle radius 9? It's r equals 0 to 3 and theta equals 0 to 2 pi. Isn't that essentially cylindrical coordinate system? But instead of using Z as the lone one, aren't we now projecting it like an X? We're going that way. Now, what will y squared plus z squared equal 9? No, let's rewind that. There we are. What will 3 lots of y squared plus z squared become in the context of this question?
3r squared.
All right. Aren't you used to 3x squared plus y squared getting you 3y squares? But strictly speaking, couldn't you switch anybody and make them the z? You could make it the z, you could make it the x, you could orientate it in the y.
Wouldn't the radius be, so you put s is bounded by x squared, y squared plus z squared equals 9.
Yeah.
But if we have 3y squared and 3.
Oh, you want to put the 9 in here to make this a number? Is that what you're thinking?
Yeah, like if you have the 3 and then you divide the 9 by 3, wouldn't you have wouldn't the radius be square root 3? Or am I going crazy here?
I think you're looking at two different things and letting them distract you. This is where the radius of the circle comes from. And this is a circle of radius 9, so that's 3. This guy down here just happens to be what the divergence is equal to. So it's not, we're not treating it the same way here. We're just treating it as an expression that can be simplified in terms of, in this case, r. So that guy goes there. And then r, dr, d theta, dx. In this case, -3, 3, 0, 2 pi, 0, and 3, and 3r cubed. And it's been a long time since we did this. Since all of these are numbers and that's 3r cubed, couldn't we actually separate this out? Aren't these variables separable? So I would do from x equals -3 to 3 of 1 dx, from theta equals 0 to 2 pi of 1 d theta, and then do r equals 0 to r equals 3 of 3r cubed dr. And that guy will get you 6. That guy will get you 2 pi. And that guy will get you 3/4 of r to the 4. So that's going to be 3/4, 3 cubed, which is 81/4. 81/4, 81 halves, 81 with 3, 243 pi. No, I'm overcounted. It's gone to them 243 over 2, so I cancelled one too many somewhere. So this one's a little bit different. It's still cylindrical coordinate scheme, but instead of the typical Z is up, which I can get away with when I'm on the Earth's surface, because Z up does kind of make sense, right? But in a general sense, out in 3D space, isn't X and Y just as likely to be up as anybody else, right? So you can rearrange your guys in all sorts of different ways. Okay, I gotta tell you a joke. My wife laughed at this, and if you know anything about me telling jokes and my wife, it's special when she laughs at my jokes. She'll have a lot of time, but not in mine. So you ready for this joke? First thing, I'll give you a background to it just quickly. One of the reputations, which is totally unfounded, is that Scottish people are very tight with their money, right? They don't like spending their money, right? And that's a stereotype, which I believe the English generated. So this American visited Scotland, and he was driving through the Highlands, and he came across a tiny little village with one pub. And the thing that attracted his attention was virtually every single person in the village was queued up outside, waiting outside the front door. And the doors, big double doors, were open. And so the American gets out his car and he goes over and he walks by everybody and he looks inside and he sees the barman there and he's cleaning glasses. And so he walks in and he says, is the pub open? Is the bar open? And the guy says, yeah, so. He says, oh, great. And he sits down and he looks behind him and he sees the prices. And it's a whiskey is 2 cents and a pint of beer is 3 cents. And he says to the barman, says, are they the real prices? And the barman said, yeah, he says it's a 100-year anniversary of this pub. So what we decided to do is put the prices of the drinks as they were 100 years ago, right, for one day. The American says, that's great. He says, I want a double whiskey and a pint of beer then. And he gets it and pays his money and he's drinking away and he's talking to the barman and he's looking around and the place is empty. So finally the American says, I noticed everybody in the village is waiting outside. He says, why? And he looks at him and says, oh, they're waiting for happy hour.
Oh man, that's terrible.
Terrible as in terribly good or just terrible?
I thought it was great.
Okay. Then if you like this one, I didn't tell my wife this one, but it's another one and it just popped in after the first one. This millionaire Scots guy, you know, the one with the really big Rolls Royces, was driving through a village in Scotland and he sees these two guys at the, you know, because he stopped at the lights, he sees these two guys at the corner eating grass. And he rains down his window and he says, what are you two doing? He says, look, we don't have any money, we've nothing to eat, so we're eating grass. And the millionaire says, oh, he says, I can't have that. He says, you come with me, get into the back of my Rolls Royce. I've got a mansion just up 2 miles up the road. I'm taking you there. So the two of them get back, you know, into the back and he's driving away and he turns around to the two of them and says, don't you guys worry. Just a couple of miles up the road, I've got a mansion. The grass is this tall. Tessa, I got a thumbs up. That was pretty impressive. I'm taking that as a victory.
2 in a row. Good
2 in a
job. You're
row.
on fire.
Well,
That's pretty
picking-
bad.
yeah, but you notice I'm picking on Scots people today. Maybe that's it. We're much better at telling jokes against each other. Okay, let's get this show back on the road then. So the last 2 questions that I want to do are 14 and 15. And these are going to challenge your memory. But we have done, well, Friday anyway, haven't we done triple integrals that just use x's, right? X equals from nothing to 2 and y is nothing to 4 and z is what to what, right? We've done them. They're the easiest ones, aren't they? You know, boxes in 3D. We've done an awful lot today where we ended up with cylindrical coordinates, right? There is one other coordinate system in triple integrals that we haven't met, and that's what the last 2 questions are about. Can you remember spherical coordinate system? Right? Spherical coordinate system. So,
R
Yes.
sine theta.
that's the one. We call it rho, but R is what it is, right? Theta and phi. Remember those guys?
The rosy pun was the best.
Rosie pun. That's true. Rosie, you still with us? Can't see you, but I know you're here. You remember that
Oh
one?
yeah, I'm here. I remember that.
Yes. Now, the surface here is the surface of a sphere. So would the solid be a solid sphere, which is pretty obvious. So these three guys are kind of screaming out, use me. Well, the radius is 3, so it goes 0 to 3. Theta goes from 0 to 2 pi. For a complete three-dimensional sphere, what are the range of phi, the last guy? The phi, phi, fo, fum guy, right? The phi. This is a
0 to pi.
memory thing. Say again?
0 to pi.
Correct. Are you comfortable with that? Right. Now, let's find the divergence. The divergence of f is if you differentiate this with respect to x, you get 3x squared. If you differentiate this with respect to y, you get 3y squared. And if you differentiate this with respect to z, you get 3z squared. And I'm going to pull out a 3, and we're going to get that guy. And so we got really, really lucky here, didn't we? In spherical coordinates, what does x squared plus y squared plus z squared get you? Yeah,
Rho squared.
You nailed it, rho squared. So we are ready to put the package together. The flux, right, that surface integral here, is going to be a triple integral of the divergence. Can anybody remember what the rest of this package is? In other words, what goes here? I'll put in the easy bit, the d rho, the d theta, the d phi. But what goes here? It should
Rho
be
squared, sine squared of that squiggly thing.
rho squared, yes, but just sine of that squiggly thing, phi.
Mhm.
Right? And the limits of integration then are going to be in the order I've got them anyway. Rho is going to go from 0 to 3. Theta is going to go from 0 to 2 pi. And finally, phi, the squiggly thing as you call it. Think faux phi, faux fum thingy. Remember that guy, phi. And what is phi? 0 to pi. So on the next page, I won't put the guys, I'll just put 0 pi, 0 2 pi, 0 3. We can kind of know who they are. This is going to be 3 rho to the 4, sine of phi, d rho, d theta, d phi. Since all of these are numbers and this here is a multiplication, can't we do separation, right? Variable separable. So the phi, which is from 0 to pi, gets that guy. The theta, which is 0 to 2 pi, doesn't really get anything. Well, I guess I could give it a 3, but I don't want to. So I'll just give it 1. And then the last guy is going to be rho equals 0 to rho equals 3 of that guy. Are we comfortable about the breakdown?
Can we just pull that 3 all the way out of all of those and just multiply it through at the end?
Yeah, that'll work. I could also have gave it to this guy and that would have worked. Actually, I could have gave it to this guy and it would have worked. Yes, that would work equally well. And this guy gets me a negative cosine from 0 to pi. This guy just gets me 2 pi And this guy gets me, yikes, 3/5 rho to the phi from 3 to 0. Okay, you plug this guy and you plug this guy in. I believe you're going to get pi on one side and a pi, and so what's that? Negative, that's 1. That's 0. That's -1. Is that 0? I don't think it is. I think it's 2. Okay. It's going to be the cosine of that guy. Take away a take away. Oh, is add. That's why I couldn't make it happen. Okay. That thing there is 2. I was kept on wondering why it was 0, because 0 didn't make sense to me. That guy's 2 pi. And that guy is 3, 6, 9, 3, well, what is it? 9, 9, and 9. 81.
Wouldn't it be 0? Because it'd be -1 plus 1.
No, it'd be the negative of -1, which is 1 plus 1.
Oh, sure. Okay.
Which was
Oh,
kind of,
right,
well,
'cause the-
yeah, that's what was happening in my head as well. I was wondering why I was getting 0 and I didn't feel like 0. Right, so that last one, I've given up trying to do that one in my head. So this guy here is going to be 3 times 3 to the power of 5, which is that guy. So it's going to be 729 over 5. And 2916 over 5 pi. So let's double check that. If you times that by 4, you get, yep, that's the right answer. Nothing pretty about that. Well, I guess it's semi-pretty. It's just a fraction of pi, but it's not that nice. Are we comfortable about spherical coordinate system is only really going to be used when the surface is a sphere or a bit of a sphere, right? So the last question is also going to be one of those. So let's get that guy set up. See how far we can get. It's the last question. Hey, so my jokes did perfect. They used up a bit of time, so we'll be finished on time. This guy is a sphere of radius capital R. All that does is it makes rho from 0 to capital R, right? So I'm pretty sure the answer is going to be some multiple of a big capital R when you're finished. It's a whole sphere, so it's 0 to 2 pi, and it's phi from 0 to pi. So limits of integration were pretty much given to you on a plate. Let's find the divergence. If you differentiate this guy with respect to x, you get 48x squared z. If you differentiate this guy with respect to y, you get 48y squared z. And if you differentiate this guy, you get 48z cubed. So far, so good. Can you see that there's a very nice common factor that they all share, which is 48z? And if I pull that out, I get x squared plus y squared plus z squared. Now, I want this to be in terms of these variables. We already know what that one is. That's a rho squared. Can anybody remember what a z gets you?
R cos theta?
I'm looking to make sure that you're right. R cos phi, rho cos phi. You did better than me because I couldn't remember myself. So rho cos phi. But isn't that the kind of thing you put down on a little cheat card somewhere and you go looking for it? So hopefully you've got a card with cylindrical coordinates on it, right? And you've got another card with spherical coordinates, including the dV, dr, you know, the conversion of what the dV is. So you'll have an R, dr, d theta, dz version, and the other one, which is the guy that's going here. So if we put this package together, we should be able to come up with the flux. So it's going to be the integral from phi equals 0 to pi, the integral of theta equals 0 to 2 pi, the integral of rho equals 0 to rho equals capital R, 48 rho cubed cosine of phi times, remember, have I got, where's my little add-on guy? Times, right, the add-on guy. So times another rho squared sine phi, and I don't have room for it, but won't the d rho d phi d theta go there, right? Just take that another line, where I can get more room in. Phi is going to go from 0 to pi, again, same with the other two guys. I have 48 rho to the 4 cosine phi sine phi, and d rho d theta d phi. Okay, everybody here is a number. Everything here is a multiplication. That means we can separate it. And I'm going to separate it like this. I get 48 here. I'm going to split it. I'm going to put a 2 here. In the middle, I've got a theta equals 0 to theta equals 2 pi. And I'm going to give it the other 24 because I want to.
Oh, okay. I see how you split. I was like, wait, where did that 2 come from?
Why did I split the 48 in particular? Why did I give this guy a 2?
Because it's actually a trig identity. That's cosine of 2. Well, in this case, it'd be 2 rho, right? Or
2 phi.
pi. I can't
So
remember
it's
my Greek
right.
letters.
It's 0 to pi of the sine of 2 guy d phi. Right? And then we've got this guy, and then we've got this guy. But I'm not even going to write these two guys down.
Excuse me.
Yes.
Should that be 48 rho to the 5th cosine phi sine phi? 2 lines up, because you've got it rho to the 4th.
Yeah. I got a 4th, and it's still a 4th because I haven't integrated it yet.
Yeah, but the line above that, you got 48 rho cubed cosine phi times phi squared sine
Yeah,
phi.
you found it. Yep. That's a 5. And I'm still not going to write it down here. But you're right, that is rho to the 5. I missed one. What's the integral of this guy?
Is it 1/2 negative
no,
cos?
no.
No.
Don't even worry about that. You're doing more than you need this. Huh? You're making it harder than it is.
Negative cos 2 phi.
No, not even that. Although that's true, what you said, there is going to be that, but I don't even need to do that. I know the answer to this integral. The final answer, not the integral and then plug in the
Oh,
numbers.
0.
Yes, agreed. And if this is 0, do I really care about this? So the final answer was just 0. And why? Because the integral, I mean, if you do it exactly, and I kept on interrupting poor Tessa because I didn't want it to keep going that road, is it would have been -1/2 the cosine of 2 theta, and you'd have plugged the numbers in. But if you have a trig function and it starts at 0 and it finishes at 2 pi, would you agree? Then won't a cosine of 2 theta or a sine of 2 theta or a 5 sine of 2 theta or any other combination, won't they all end up being 0? Because the start and finish value will be the same number. In fact, no, I was going to say, is that true? That true for secants? Yeah, it would be. It would even be true for secant 2 thetas and tan and all sorts of other ones, right? You know, the bit above is exactly the same as the bit below, kind of the trigs. Bottom line is the integral is 0. So the flux of this vector field. So if you imagine a sphere floating inside that vector field, then all the things hitting the surface going in is exactly balanced by the same amount of things going out. That would be a perfectly balanced system. If you think of the vector field as being wind, right? Then wouldn't that ball, if there was no gravity involved, wouldn't that spherical ball just stay exactly where it is? Right, because the stuff coming in would be balanced by the stuff going out, so the forces would be equally balanced. So we would say that system was in equilibrium, is the fancy name for it. Equilibrium systems are good. Aren't equilibrium things balanced? Right? You wouldn't want to build a bridge that was too top heavy, because well, in certain directions it's okay. I think going down the road, it's okay. But you wouldn't want a bridge that had a tendency to go left on you, would you? That would not be a safe structure. So I don't know if that's a good analogy. Put your last names down and bye-bye for now.